August 1940, the skies above Britain swarmed with German bombers, the ominous droning of Heinkel and Junkers aircraft filling the humid air as the Royal Navy's anti-aircraft batteries unleashed a torrent of shells, tens of thousands in a single engagement, each explosion echoing across the coastline while pilots and gunners prayed that sheer volume would bring down even one enemy plane. A hope that was tragically mathematical in its futility, as calculations revealed that at current rates, the Allies risked exhausting their ammunition before Germany would ever be forced to pause, a stark and terrifying reality that crystallized the nature of modern aerial warfare. Speed and massed firepower alone could not overcome the efficiency of mechanized, coordinated attacks from the air, and this brutal arithmetic formed the backdrop against which men like Dr. Merle Tvedt, a 39-year-old physicist at the Carnegie Institution, began to think unconventionally, to imagine possibilities so audacious that military officials dismissed them outright, as Tvedt, short-tempered, brilliant, and fiercely independent, proposed the impossible: to build a miniature radar set, so small it could be packed into the nose of an artillery shell, yet robust enough to survive the extraordinary forces of gunfire, accelerating at 20,000 g-forces within milliseconds, to detect the presence of a target within 70 feet and detonate precisely without ever visually identifying it, a concept that, on paper, violated every engineering principle of the age, considering that vacuum tubes were large, fragile glass bulbs, radios weighed hundreds of pounds, and artillery shells traveled at such speeds and endured such accelerations that conventional electronics would be obliterated. Yet Tvedt, who had spent years studying radio wave propagation and the delicate physics of atmospheric phenomena, understood the fundamental principles that could make such an endeavor feasible, and while military brass scoffed at the idea as impossible, the events of December 7, 1941, the devastating Japanese attack on Pearl Harbor, removed any lingering doubts about the need for radical innovation, as American anti-aircraft gunners, firing time-fused shells blindly into the sky, inadvertently caused civilian casualties in Honolulu. The irony of friendly fire underscoring the inadequacy of conventional artillery, and within hours, Tvedt Section T received unprecedented support, unlimited funding, unrestricted access to personnel, and the simple, stark directive to make the impossible work, or watch the war be lost, a task that transformed his already ambitious project into a national imperative, for the fate of millions now depended on finding a solution to a problem that had defied generations of engineers and mathematicians alike, a challenge that demanded ingenuity, precision, and relentless experimentation, as the British Tizard mission had previously revealed, bringing secrets from radar research, jet engine designs, and early proximity fuse concepts, which American scientists initially dismissed as fanciful, but which Tvedt recognized as the theoretical foundation for a practical, battlefield-ready weapon, and he began assembling a team of exceptional specialists, vacuum tube miniaturization experts who understood the limits of glass and electron flow, mechanical engineers capable of designing resilient components that could survive shock and rotational stress, and chemists who could create batteries that would activate reliably under extreme acceleration, all working in utmost secrecy under the National Defense Research Committee, guided by Vannevar Bush, and despite early setbacks, tubes shattering instantly under acceleration, batteries failing under centrifugal forces, circuits collapsing under temperature extremes, the team learned from each failure, developing flexible glass tubes that bent rather than broke, dry chemical batteries activated by gun blast, and protective wax formulations that stabilized fragile electronics mid-flight, until in the spring of 1942, fully integrated proximity fuses survived naval gun firings and detonated at precisely calculated distances, turning near misses into certain kills, a miniature radar miracle contained within a shell no larger than a coffee cup, capable of surviving forces that would obliterate much larger devices. And by summer, production challenges required mobilizing factories nationwide, retooling existing production lines, and coordinating across dozens of companies, including Crossley Corporation, RCA, General Electric, and even Wurlitzer, with industrial engineers, machinists, and assembly workers collaborating to mass-produce what had once seemed impossible, and the first tests aboard USS Cleveland in Chesapeake Bay validated the concept as drone aircraft were destroyed by lethal air bursts, proving that American anti-aircraft fire had been transformed from a desperate, low-probability gamble into a precision weapon, with Lieutenant Red Cochran aboard USS Helena demonstrating the system's effectiveness against Japanese Val dive bombers, as shells detonated with perfect timing, shredding airframes without the need for direct hits, creating defensive envelopes that enemy pilots could neither penetrate nor anticipate, and the strategic implications were staggering, as Allied ships could now defend themselves with unprecedented accuracy, transforming naval warfare from reactive survival into proactive control of airspace, while strict security protocols ensured that proximity fuses remained a closely guarded secret, used only over water to prevent enemy recovery, and yet the technology's impact extended far beyond the Pacific, as British batteries defending London against V-1 flying bombs were soon equipped with American VT fuses, raising interception success from 17% to 74% within weeks, turning the tide against Germany's terror weapons and neutralizing attacks that had once seemed unstoppable and the same transformative principles later reshaped land combat during the Battle of the Bulge, when Colonel George Axelson, confronted with hundreds of thousands of proximity-fused shells yet prohibited from using them by Pentagon regulations, ultimately defied orders to protect American soldiers, unleashing devastating air bursts against advancing German infantry that shattered formations, inflicted catastrophic casualties, and created unprecedented psychological terror, as enemy troops realized that American artillery could now kill what it could not see, rendering traditional countermeasures obsolete, and over the ensuing months, the proliferation of proximity fuses throughout Allied forces created a fundamental shift in battlefield dynamics, allowing commanders to engage targets with precision that redefined tactical calculations, tripling anti-aircraft effectiveness without additional guns, neutralizing Hitler's vengeance weapons, and forcing German pilots and artillery units to adapt to defensive technology that anticipated their every move, fundamentally altering the mathematics of war, while the personal ingenuity, perseverance, and technical mastery of Tveit, Van Allen, and the countless engineers, machinists, and military personnel who implemented the vision demonstrated the profound impact of human creativity in the crucible of global conflict, proving that audacious scientific innovation, guided by necessity and supported by industrial capacity, could change the outcome of a war, save millions of lives, and establish a legacy of technological superiority that reverberated long after the guns fell silent, as every aspect of the proximity fuse, from the miniature vacuum tubes to the centrifugal force-activated batteries to the wax-embedded circuits, represented a triumph over limitations that had once seemed absolute, a testament to the power of experimentation, interdisciplinary collaboration, and the relentless pursuit of solutions to problems that initially appeared insurmountable, and by the end of 1944, with Allied forces equipped with these revolutionary weapons, every theater of war experienced a transformation, from the skies over London and Antwerp to the forests of the Ardennes, as enemy strategies crumbled in the face of precise, indirect, yet deadly artillery, and the mathematics of combat itself were rewritten, demonstrating that one brilliant idea, pursued with dogged determination and unflinching resolve, could indeed change the world.